We will first see what is a signal, then we will see what is an analog signal, a discrete time signal, and then we will see what is a digital signal, so that we can start our digital electronics course. So let's move to the signal. What it is: a signal is a function that represents the variation of a physical quantity with respect to any parameter. This any parameter is the independent quantity, and it is generally time or distance. So the function is definitely dependent upon this independent quantity, and I hope you already know about the function from your mathematics course, but we will also see one example that will clear these things more. So let's say my function is f, and as it is dependent upon the independent quantity, and I will say my independent quantity is x, then I will write it as f x. This shows that this function is dependent on the x, and let's say it is equal to minus of a x square plus bx plus c. Now this is my function, and I will try to implement this function in a daily life example. For this I will take a boy. Let's have a boy, and this boy will do a work for us. He will go to a particular place and measure the temperature from morning 9 a.m. to the evening 9 p.m. So he's having his thermometer. He will stand there and he will measure the temperature in every 1 minute. So I can say he will have a data at the end of the day from 9 a.m. then 9:01, 9:02, like at 9 a.m. he is having 27 degrees Celsius, then 9:01 is having 27.5 degrees Celsius. In the same way, he will have the different temperature for different time till the 9 p.m. So this is his task, and he will have a data, he will have a list of the temperatures for a different time. Now what we can do with this information? We can plot it. So let's try to plot it. And you already know that this x-axis we use for the independent quantity, and this y-axis we use for the dependent quantity. And in this case the independent quantity is time. Definitely the time is independent. I will represent it by small t, and this axis will represent my temperature. T, capital T, is my temperature, and as it is dependent on the time, I will write t here. Now we can plot these values. Let's say our origin is 6 a.m. and this point is 11 p.m. This is a 9 a.m. and this one here is 9 p.m. So we will just show the temperature for the different times, and let's say it comes like this, and then we can join these points and we will have our function like this. So this particular function is the downward parabola, and it is having the equation like minus of a t square plus bt plus c. This minus of a shows that we will have a downward parabola, and there is one condition for that: this a must be greater than 0. If this a is equal to 0, we will have a straight line, because t will be equal to bt plus c. This is the equation of a straight line, y equals to mx plus c. This c is the intercept, and if this a is less than 0, we will have the upward parabola. So this is a little bit about the functions. You have already learned these things in your mathematics back in the 11th standard, so we'll not go much into that. And finally you can have your signal. This function is your signal. You will have the values of the temperature for the different time, and that is what the signal. You will have a pattern that will tell you how the temperature has been changing from 9 a.m. to 9 p.m. So this is what you have to remember about the signals. Now I will narrow down this study of this signal, and I will talk especially about the electrical and electronics. And in electrical and electronics, usually the signal is the variation of the electrical quantity, generally current or voltage, with time. So it's important to write this thing, and let's write it down. in electrical and electronics, usually signal is variation. You can see here we are having the variation of the temperature with time. In the same way, we have the variation of the electrical quantity, and this electrical quantity is generally current or voltage. And what is the independent quantity in this case? The independent quantity is time. So this variation of electrical quantity, generally current or voltage, is with time. So this is something you have to keep in your mind. And there is one very important point that you must know. If the current or the voltage remains the same for different time, then it is not a signal, it is a direct value. For example, if I talk about the current, and if current is same for the different time, then it is direct current. It is not a signal, it is a direct current. And we can say di, the small change in the current, is equal to 0. The current is not changing, and you can plot it simply like this. The current at T1, let's say this is T1, is I naught, and current at T2 is also I naught. So the current is not changing, it is a direct value, and thus it is not a signal. Signal must vary with the independent quantity. And let's talk about the transducers a little bit. So the transducers are the device which is used to convert the non-electrical signal to an electrical signal, and the reverse transducer is the device that is used to convert the electrical signal to the non-electrical one. And let's see one example for it. If you are singing a song, you require a mic. This one is the mic, okay, and you are singing near to it, so that your sound is converted to the electrical energy. This sound creates some vibration, and that vibration is converted into the electrical pulses, and that electrical pulses is amplified. There is a device that we call as the amplifier, because definitely it is required to amplify the signal so that it can be converted and interpreted well. So we have an amplifier, and once this amplifier is there, it will amplify, and then you have a speaker. The speaker is there, and then again the sound energy is given back. So sound energy is given in, it is converted to the electrical energy, it is processed well, and then again it is given back as the sound energy by the means of the speaker. So this is how the signal works, and it is a very small explanation for the signal. There are so many hundreds and thousands of types of signal available to us, and we have just saw one example for the temperature. Now in the next presentation we will see what is the analog signal and the discrete time signal. Then finally we can have our digital signal. So this is all for this presentation. See you in the next one. In the last presentation, we completed the introduction of the signals, and I also gave you one example in which we varied the temperature from 9 AM in the morning to the 9 PM at the night. I also told you in electrical and electronics, the signal is nothing special but the change in the current and voltage with time. So in this presentation, we will move forward with our signals, and we will see what is an analog signal. Before actually going to the actual idea, let me first tell you the difference between the analog clock and the digital clock. Why we call this analog and why we call this digital. So let me write it down. This one is the analog clock, and this one is digital clock. So let's first talk about this analog clock. In this you can see we have three hands. The first one, this one is the hours hand, this one is the minutes hand, and the small one is the seconds hand. So we can say that this analog clock or this clock can have the time as hour, then minute, and then seconds. So it can take any value in 24 hours. Now let's see what happens in the case of digital clock. This one represents hour and this one represents the minute, but there is no second in this case. Once we have 60 seconds passed, this 12 will change to, and we have 13. We cannot see what is going in between this 12 and 13 because it is not allowed in the digital clock. Either we have 11, 12, 13, 14, 15, not 11 minutes and 10 seconds. It is not allowed. That's why this is digital, because in digital we have certain levels like this. Let's say this is 11 minute, 12 minute, 13 and then 14. Either you will be on 11 or 12 or 13 or 14. You cannot be in between 11 or 12. Like this is 11 minutes and 30 seconds. You cannot have the value equal to 11 minutes and 30 seconds because second is not allowed. This level, this intermediate level is not allowed in digital clock. On the other hand, in analog clock we can have 11 minutes and 30 seconds definitely. That's why we call it analog, because it is analogous to the time. We have every values in the given limit. So this is a small thing which will help you to understand the analog and digital signals. Now let's move to the actual thing here. You can see Tmax. Tmax is the maximum temperature, and let's say this plot or this graph is for the temperature, and we are measuring the temperature from the first of the month, and this one is for the last day of the month, that is 31st, and we are measuring the temperature like this. Let's say for any reason like rain or something, we have the temperature lower from the 16th of the month. So this is the plot, and we can see that this particular plot is analogous. This one is analog. Why this is analog? Because you can see that each and every value is possible. From 0 to Tmax, the temperature in, let's say, degrees Celsius, we can have any value. Like this one is 27 degrees Celsius, and we can have 27.8 degrees Celsius. In the same way we can have 27.88 degrees Celsius, and all the intermediate values is allowed, and let's say Tmax is 47 degrees Celsius. So from 0 degrees Celsius we can have any value between the 47 degrees Celsius. So this one is analog because it can take any value within the given limit. So analog signal is the signal which can take any value within the given limit. Now as we are talking about the digital electronics, let's change this Tmax by the Vmax. This Tmax is Vmax. Vmax is my voltage, and this is 0 volt and this is V volt, that is the maximum voltage, and let's say Vmax is 20 volts. So it can take any value between 0 and 20 volts because it is an analog signal. Now we can move to the next type of signal, that is the discrete time signal. So let's study what is a discrete time signal, because it is important to understand this signal before we move to the digital signals. So let's see what is the discrete time signal. The signal which is defined for the discrete interval of time is called as the discrete time signal. So I will write this thing down so that you can have a better or proper definition of the discrete time signal. The signal which is defined, which is defined for the discrete intervals of time is called as the discrete time signal. Now let's understand it with the help of this graph. Before that I will clear some space so that we can understand it easily. Okay, I will copy this down and then we can analyze it. So let's copy and then paste. I will drag it down and now we can analyze it. In discrete time signal, the time axis, that is my x-axis, is discretized. By discretized I mean, let's say we are measuring the temperature on 11 o'clock daily. So this is the 11 o'clock of the first day, then this is for the second day, and this is for the last day, and this one is for the second last day. These are for the different days and all are on the 11 a.m. So what between the 11 a.m. of the first day and the 11 a.m. of the second day? We don't know. What is the temperature between the 11 a.m. of the first day and the 11 a.m. of the second day? So this definition, this value of the temperature is not available to us, so I have to remove it. So let's rub it down. Okay, in the same way, we don't have the value of the temperature between the 11 a.m. of the last day and the second last day, and the same thing will be applicable for the other days of the month. So this is how a discrete time signal looks. We have discretized the time axis. This is not proper, but you can draw it proper, and in the same way we have to eliminate these portions also. Now this one is the discrete time signal. We have the definition of the function. In this case it is the temperature for the discrete time values. Let's say this is t1, this one is t0, t2, all the way to tn. So we have the value of the function at t0, then t1, t2, all the way to tn. The value of the function we have for this times only. What is between t0 and t1? We don't know, because we have not monitored the function for that particular time. So this is what a discrete time signal looks, and you have to know one thing, that the signal is actually analog. The change is definitely analog, but we have not monitored this particular sections, so we have a discrete time signal, and the discrete time signal is the subset of analog signal. So this is an important thing to know, and all real life signals are analog signal. And I think this is all. We are already pushing the time, and we have learned two things. The first one is the analog signal, and the second one is discrete time signal. In the last presentation, we completed analog and discrete time signal. In this lecture, we will study digital signal. In digital signals, we discretize both time and magnitude. We have to discretize both time and magnitude axis. If you remember the discrete time signals, we discretize the time axis but not magnitude. But in case of digital signals, we have to discretize the magnitude axis as well. By discretization, I mean we have to divide the time axis in equal intervals. If delta t is the interval, then we can find out this interval delta t by t1 minus t0, or we can have t2 minus t1. In the same way, tn minus 1. This is how we can find the interval. Now the next thing that we have to do is to discretize the magnitude axis also. This is a very simple example in which we are trying to measure the temperature of a city. Capital T is the temperature, and this is in degrees Celsius. Small t is the time in seconds, and we are measuring the temperature at T1, T2, T3, T4 and T5. If I consider the case of discrete time signals, then let's see what we have. The temperature at time T1 is equal to 9 degrees Celsius. You can clearly see it is equal to 9 degrees Celsius. We have not discretized the magnitude axis, so the temperature can take any value from 0 to 45. Every value is allowed from 0 to 45. So 9 degrees Celsius is absolutely allowed. For T2 we have 38 degrees Celsius. For T3 we have 24 degrees Celsius. For T4 we have 15 degrees Celsius. and for T5 we have 45 degrees Celsius. And this is for discrete time signal, right? Now we will consider the case of digital signal, and we have to discretize this magnitude axis also. So let's do it. I'm going to discretize this, and I will have the next level equal to 15 degrees Celsius and another level equal to 30 degrees Celsius. So we have 0, 15, 30, 45 as the allowed values for the temperature capital T. This temperature can take values equal to 0, 15, 30, 30 and 45 only. We divide the magnitude axis into fixed number of levels, and the signal can take value equal to these levels only. This line is very important, the most important part that you have to remember in digital signals. This signal can take value equal to these levels only, right? Now we will consider the same case, the same temperatures for the same time, and we have to find out what is the value for temperature capital T at these times. We are considering the digital signal in this case. So let's start. Temperature T at time T1. At T1 we have 9 degrees Celsius, but 9 is not allowed. It is between 0 and 15. It is between 0 and 15. Now what we have to take, 0 or 15? The difference between 0 and 9 is 9 degrees Celsius, and the difference between 9 and 15 is 6 degrees Celsius. So this 9 degrees Celsius is near to 15 degrees Celsius. So at first sight it seems we have to consider 15 degrees Celsius, but this is not true. To minimize the error, we have to take the lower value. We have to take 0 degrees Celsius. This is the key point that you should remember. We don't select the higher value, we select the lower value. So the temperature T at time T1 is equal to 0 degrees Celsius, and the temperature T at time T2 is 38, but 38 is also not allowed. It is between 30, 30 and 45. We again have to take 30, 30 because this is the lower level. So at T2 we have 30 degrees Celsius. Temperature T at T3 is equal to, at T3 we have 24. 24 is near to 30, but again we have to consider the lower level. So 15 degrees Celsius is the answer. At T4 we have 15. 15 is definitely allowed, so we have 15 degrees Celsius. At T5 we have 45, and 45 is allowed, so 45 degrees Celsius. And this is the values in case of digital signal. So you can clearly see the difference between discrete time signals and digital signals. We can have any value of the temperature within 0 to 45, but in this case we have the value for temperature equal to these levels only. Now we will see one more example in which we will consider the voltage. This is the time axis. Capital V is the voltage. We are considering the digital signal, and we have 0 volts and 5 volts as the two values that are allowed. Let's say at any time T1 the voltage is equal to 2 volts, then voltage at T1 is equal to 0 volts, because I have already explained you we have to consider the lower value, so I have taken 0 volts. Now you can see we have error of 2 volts because the observed voltage was 2 volts, but we are getting 0 volts. So how to overcome this error? We can overcome this error by increasing the number of levels. If we increase the number of levels, error will reduce. This is very important point, very important point. On increasing the number of levels, error will reduce. Let's see how. I'm going to divide 0 to 5 in 4 equal parts. So I will have 1.25 as the next level, 2.5 and 3.75. okay, these are the levels. So we now have 0, 1.25, 2.5, 3.75 and 5 as the allowed values for this voltage V. So voltage at time t1 is equal to 1.25 volts, because we have to consider the lower value, and 2 volt is between 1.25 and 2.5. Now we can easily take 1.25 instead of 0. So the error is reduced, and now we have error of 0.75 volts only. Earlier the error was 2 volts, but now the error is 0.75. If we increase the number of levels more, for example, if I have levels equal to 0, 1, 2, 3, 4 and 5, then this 2 volt can clearly be measured as 2 volts. So voltage at T1 in this case is equal to 2 volts, and error of 0 volts is there. So we have reduced the error of 2 volts to 0 volts by increasing the number of levels. This is all for this presentation.
Modulation. We often hear this word when speaking about communication systems. It is a simple concept, often overlooked or misunderstood, but very important to understand since it forms the base for wireless communications. In this video, we will see what is modulation, its basic types and importance of modulation. Generally, when we describe a signal, we talk about its three important characteristics: frequency, amplitude, and phase. Modulation is a simple process in which a carrier signal of constant phase, frequency, and amplitude is modified by non-linear input signal. As a result, we will have a signal output which changes its characteristics corresponding with modulating signal. In most wireless communication systems, audio signal of frequency ranging from 20 Hz to 20 kHz will be used as modulating signal. Now let's take a look at the three basic types of modulation. Frequency modulation. In this type of modulation, frequency of the carrier signal will be altered with respect to modulating signal. As a result, we will obtain modified frequency signal in output. Amplitude modulation. Here, amplitude of carrier signal will be altered with respect to modulating signal, and we will get amplitude modified signal as output. Phase modulation. Phase of the carrier signal will be modified in this method, and we will obtain phase modified signal in the output. Apart from these three, there are many other modulation techniques like DSP, SSP, VSP, QAM, ASK, FSK, PSK, and much more. Let's take a look at the three main advantages of modulation. Number 1. To transmit the signal to long distances. Low frequency signals like audio or any other signals are incapable of propagating to long distance on their own. When modulating them with a high frequency carrier signal, the modulated output will obtain high frequency characteristics, and as a result, it can propagate longer and in turn provides more range to the user. Modulation works the same way as paper and stone, where the high frequency carrier signal provides the ability to reach longer distance for audio signal. Number 2. To reduce the size of antenna. Antennas are used to propagate the signals into atmosphere. Consider an unmodulated audio signal of frequency 20 kHz. The antenna height for propagating this signal would be of 3.75 km, and it's totally impossible to build such antenna. However, if you modulate them to 1 MHz, then you need an antenna of 7.5 meters only. That is totally possible. Number 3. Avoid mixing of signals. We all know that frequency of audio signal ranges from 20 Hz to 20 kHz. So if two devices send out unmodulated audio signals, it will result in mixing, and eventually the receiver will receive some gibberish audio which will be of no use. But when modulated, signal from device 1 and 2 will propagate in individual reserved bands and therefore preventing the audio signal from mixing.
Hello everyone. Welcome to another video. In this video we are going to talk about different transmission types that are used in networking, and those types are Simplex, Half-Duplex, and Full-Duplex. So let's talk about one by one. First we can talk about Simplex. In Simplex transmissions, data is sent in one direction only. Think of it as a one-way street where traffic can only drive in one direction down it. An example is a television broadcast, where data is transmitted to receiving televisions, so only one-way transmission take place. Another example of Simplex transmission is data being sent from a computer to a printer. Here data is sending only one direction. Half-duplex transmissions, data is sent in both directions, but only one direction at a time. So if computer A is sending data to computer B has to wait until computer A is done before it can send data to computer A. So data flows in one direction at a time. An example of half-duplex is just like how walkie-talkies work. With walkie-talkies, a person has to press a button if they want to talk to transmit their voice to the other person. And while the button is pressed, information is only going in one direction, so they can't hear the other person while they're transmitting their voice. They would have to release the button in order to receive the other person's transmission. Full-duplex transmissions, data is sent in both directions at the same time. An example is a telephone conversation where both people can speak to each other at the same time. Another example is broadband connection on a phone line. So, as a comparison between Simplex, Half-Duplex, and Full-Duplex, you can use an analogy of cars on a highway, where you have cars that travel only in one-way direction, can be considered as Simplex data transmission. Where you have cars that across an area, so when a half-duplex, the cars would all have to share a single lane on the highway, and that lane only allows traffic in one direction at a time. But in a full-duplex, the cars don't have to wait, because you can compare a full-duplex as having a two-lane highway. Each lane is dedicated for a direction. The cars that are traveling in the opposite directions have their own dedicated lane as they travel to their destination.
We've looked at two communication methods already, parallel and serial transmission, and two separate methods, like the two pairs are separate. We've got now synchronous or asynchronous transmission. And synchronous as a term means occurring at the same time. If you think of synchronized swimmers or synchronized divers, all of their actions are occurring at the same time. So unsurprisingly, for this communication, this is where the sender and receiver are kept synchronized throughout. And this is done by them using a clock which is at the same rate. So they're essentially using the same clock signal or a replica of the same clock. And this is used as a reference point for the data transmission. And this means transmission occurs at regular intervals. To show this visually then, if we have two devices, the sender and the receiver, they both have access to the same clock, or as I say, a replica of the same clock. A clock is just a device that produces a repeated signal, so it fluctuates between two different values, two different voltage levels, and it can be used in this way to regulate transmission because it occurs at regular intervals. So every 10 milliseconds it fluctuates between being high to low. So in this example, let's say that they've both agreed that when the clock is high, this device is going to send data to this device. It could be when the clock is on an edge, it could be when it's at low. Doesn't really matter. But we've agreed here that this device is going to send data when the clock is high, like it is now. At the beginning it's high. So we send data, and then once the clock is low again, once it fluctuates, it's going to stop sending data. It doesn't send data when the clock is low. This allows the device to be ready to receive it, and it just regulates the whole transfer essentially. And it's very unlikely that this is going to be enough time to send all the data that's needed, so it will just sort of fluctuate between sending data and then waiting for the clock to return to its other position. Asynchronous, on the other hand, does not use a common timing signal to a common clock. Asynchronous meaning not synchronous. So here the devices aren't kept synced, they're not permanently synced up. They only are synced up during transmission. And this is done using a start bit at the beginning of the message and ending it with a stop bit. So two devices again, and it's sending data whenever it wants to, but it adds a start bit to the end, to the front even, and adds a stop bit to the end. And usually 1 is for the start bit and usually 0 is for the stop bit, but it doesn't really matter either way. The actual message has to be a set length, so they have to have agreed that a byte is going to get sent, so it can count the bits. It knows it's going to get 10 bits in total because it's got the stop bit and the start bit as well. So I glossed over it, but this bit here is important. The fact they are synced up during transmission. You know, when no data is being sent, they're not synced up at all. They've both got separate clocks, but they do need to be synced up during transmission because this device is sending data at a set rate. It's going, okay, it's going to be 1, 0, 1, 0, so at a set rate, and this rate might not match up with this computer. Once the start bit arrives, it can essentially time the difference between the start bit and the first actual bit of the message and use that time to sync up its own clock so that it's operating at the same rate as the sending device. And otherwise it might miss bits, it might miscount how many bits are in the message, so it's really important they are synced up, if only during the transmission itself. And as I say, the size of the body of the data must also be pre-agreed. It needs to know there's going to be a byte, otherwise it won't be able to interpret whether this final bit is part of a message still or is in fact a stop bit. And what's also important is a gap will be left between the stop bit and any next message. Likely there's going to be a second message, and it will leave a gap in between so that it doesn't seem like it's just another message straight on. It needs to have a slight gap. Comparing the two then, so synchronous is usually faster than asynchronous because asynchronous has the extra bits which don't seem like too much of a big deal, but when you're dealing with very small messages, often a message is just a byte. You know, it's a fairly high percentage of the actual overall message. You know, it's a fifth of a message you're spending on just the stop and start bits. And also the gap needed, let's go back in, the gap needed after the stop bit counts as slowing it down. So synchronous is usually faster. Also, synchronous does need a common clock signal or some way of sharing it, and within a single device where a clock signal is going to all the components, that's quite simple, but with two separate devices, getting a common clock signal is not very easy to do, so that's why asynchronous might be better in that case. You don't have to share the clock, it's cheaper and easier to implement. For synchronous, you may also have to wait briefly until data can be sent. You're waiting for the clock to go back to its position which you're allowed to send data at, and that's going to be a very small amount of time. If you're sending multiple messages over multiple clock cycles, that delay may build up, but it is still faster overall despite having to potentially wait a little bit before sending it. You can't send it when you want, whereas asynchronous can transmit whenever you're ready. You don't have to wait for the other device to be ready, you just send it whenever you want to. So synchronous and asynchronous terms are separate to serial or parallel, but to try and link them together, almost all parallel transmission is actually synchronous. We talked about how the bits have to arrive simultaneously, and synchronous really lends it to this. It's really keeping them on the same page. Also, because parallel transmission has to be done over very small distances, it's possible to have a common clock signal. So if it's done within a computer like we talked about, then the CPU and the memory are going to have access to the same clock signal. We don't have that technical constraint when devices are kept separate. Asynchronous is definitely more prevalent, just worldwide. We don't have the same clock signal we can all tap into, but within a single system where there may be synchronous communication going on, it might be used when data is sent sporadically. So a mouse or a keyboard, the input from a mouse or a keyboard isn't regular, it's sporadic. We don't know when someone's going to press a key on a keyboard, so it may as well be asynchronous. You don't want to keep them linked up when we don't need it necessarily.
Today I will talk about the 3 multiplexing methods: time division multiplexing, statistical time division multiplexing, and frequency division multiplexing. The Latin root plex means woven together or twisted together. For example, the word complex means many different parts are twisted together to make a thing complicated. Multiplexing in network means multiple signals are combined together and thus travel simultaneously over one link. Thus, the purpose of multiplexing is about sharing. TDM is transmitting different users' digital signals over one link or one media by dividing time into slots or intervals and assigning them equally among these different users. Let's look at one example. Suppose there are 3 different users to send their data. At the transmission end, the multiplexer divides time into different segments, which we call time slots or intervals, and assign them equally. They can be sent simultaneously. At the receiving end, the demultiplexer separates them. The main feature of TDM is equality. Every user is allocated with the same amount of time, but equality is not efficient in many situations. For example, some users may have more data or higher priority than others. Giving the same amount of time regardless of their need and priority is not cost-effective. That's why we need a new method, statistical TDM, or simply statistical multiplexing. Statistical multiplexing analyzes statistics related to the workload, need, or priority and determines on the fly how much time each user should get. Let's take a look at the same example, but this time the user B has more data to send or has higher priority than both user A and user C. The multiplexer decides to give user B most time slots and the least time slots to the user A. Compared with the time division multiplexing, we can say statistical multiplexing is more efficient and more in control. FDM is a different multiplexing technique. It deals with analog signals, not digital signals. Look at this example. 3 different users are sending their data over the same channel. FDM combines these signals together and sends them simultaneously as they travel separately in their own non-overlapping subchannels. In summary, FDM is about a frequency channel and each user uses its own non-overlapping frequency channel. TDM is about time allocation. Every user is given with the same amount of time in TDM or different amount of time in statistical multiplexing. You may ask, when do we use TDM and when do we use FDM? To answer this question, we need to know about baseband and broadband. Baseband deals with digital signals. Baseband systems can transmit only one signal at a time. Digital signals occupy the entire bandwidth, which means baseband systems requires an exclusive use of the channel's capacity. When I use a wire, no one else can use it at the same time. Ethernet is an example of a baseband system. TDM and statistical TDM are used in baseband system. Broadband transmissions deal with analog signals, which are in the form of optical or radio frequency waves. Broadband allows multiple transmissions at the same time. They can share one channel by using different frequency range. Thus, FDM is used in the broadband system.